Introduction. Dad, I'm looking at this compass you bought me for my birthday. It is such a good device. But something happened and I'm unable to figure why that has happened. Can you help me, Dad? Yes, Rajiv. Tell me exactly what happened. I took the compass to my friend's place. They have some electric work being done in their house. We were playing with the compass very close to an open wire. Suddenly, for no reason, the compass needle got deflected. When we moved away from the wire, it came back to where it was. Why did that happen? That happened because electric current acts like a magnet and produces a magnetic effect. Children, in this lesson, we will learn about magnetic fields, electromagnetic effects, electric motors, and electric generators. Objectives. At the end of this lesson, you'll be able to identify magnetic fields and field lines, describe the force on a current-carrying conductor in a magnetic field, explain an electric motor, explain electromagnetic induction, describe an electromagnetic generator, identify domestic electric circuits, overview of magnetic fields and field lines. A magnetic field is created by the magnetic influence of an electric current and magnetic material. Our planet Earth produces its own magnetic field, which is an important factor during navigation. Magnetic fields are also used in electric devices such as transformers. Magnetic field lines can be compared to the constant altitude lines that are visible on a map. Magnetic field lines help in stating simple concepts of magnetism easily. These are defined as the number of field lines through a surface. These can be easily transformed into a mathematical format. Magnetic field lines are visually displayed in polar auroras where visible streaks of lines are created along the direction of Earth's magnetic field. Current-carrying conductor. An electric current passing through a metallic conductor results in a magnetic field being created around it. The charge of the current-carrying conductor placed in a magnetic field experiences a separation in a direction that is perpendicular to the current and the magnetic field. This results in a voltage whose direction is proportional to the applied magnetic field. This effect can also be reversed. Magnetic field. Current through a straight conductor. As you have seen earlier, let us see what happens when we change the current that is passing through the wire. The effect on the compass also varies. So, if you increase the current, the deflection of the needle of compass will increase. From this we know that the magnitude of the magnetic field produced at any given point will increase as the current through the wire increases. Now try moving the compass away from the current passing through the wire. You will see that the magnetic field produced by a given current in the conductor decreases as the distance from the compass and the wire increases. Maxwell's corkscrew rule. Maxwell's corkscrew rule, also known as right-hand thumb rule, defines that moving a corkscrew in the direction of current moves the direction of magnetic field along with the direction of current vertically downwards. If we move the corkscrew downwards in the direction of current and the handle of corkscrew is turned in the clockwise direction, then the direction of the magnetic fields is in the clockwise direction. So, when current flows upwards, the direction of magnetic field changes and is anti-clockwise. Magnetic field. Current through a circular loop. Let us now look at what happens when the wire through which we passed the current is placed in a circular manner. The magnetic field around it is generated in the form of concentric circles. Try moving the bar magnet away from the wire slowly. By the time we reach the center of the loop, the concentric circles appear as straight lines. The entire magnetic field appears as a straight line. Now try applying Maxwell's corkscrew rule to this and check whether every section of the wire is able to generate magnetic field lines in the same direction. Magnetic field. Current in a solenoid. A solenoid is a current-carrying wire that is coiled closely into a shape of a cylinder with the turns as close together as possible. This is similar to a bar magnet. Each solenoid has a north pole and south pole. The magnetic field lines inside a solenoid are straight lines and indicate that the magnetic field is similar at all points in the solenoid. This strong magnetic field in the solenoid can be used to magnetize magnetic materials. This type of a magnet is called an electromagnet. Force of current-carrying conductor. We have seen that an electric current that flows through a conductor produces a magnetic field. The magnetic field so produced exerts a force on a bar magnet placed close to the conductor. French scientist André-Marie Ampère, 1775 to 1836, discovered that the bar magnet would also exert an equal and opposite force on the conductor. Fleming's left-hand rule. Fleming's left-hand rule is mnemonic to represent 3 directions. You need to stretch your thumb, forefinger, and middle finger of your left hand. Each finger points to a specific direction. The forefinger points in the direction of the magnetic field. The middle finger points to the direction of the current. The thumb points to the direction of the motion. This is Fleming's left-hand rule. Examples include woofers, subwoofers, electrical actuators, etc. Electric motor. An electric motor is an electromechanical device. It converts electrical energy into mechanical energy. Let us look at how electric motors work. A motor uses magnets to create motion. Inside an electric motor, the attracting and repelling forces of a magnet create rotational motion. Fans, blowers, and pumps, disc drives, etc. are some examples of electric motors. Electromagnetic induction. The production of an electric current across a conductor moving through a magnetic field is called as electromagnetic induction. For example, generators, transformers, induction motors, electrical motors, synchronous motors, and solenoids all use electromagnetic induction. Michael Faraday was a British scientist, chemist, physicist, and philosopher who discovered the magnetic field, electromagnetic induction, diamagnetism, and electrolysis. His experiments included the discovery of generating currents by moving a magnet. Let us try sliding a bar magnet in and out of a coil of wires. You see that the wires generate a current. This is known as electromagnetic induction. Electric generator. An electric generator converts mechanical energy to electrical energy. It forces electrical charge to flow through an external electrical circuit. Examples include a water pump, which causes water to flow but do not create water. Electric generators operate based on electromagnetic induction, that is, whenever a conductor moves to a magnetic field, a current is induced in this conductor. If a magnet is spinning inside a coil, alternating current is induced in the coil. Alternating current changes direction after equal intervals of time. The other type of current is direct current, which does not change direction with time. Domestic electric circuits. Electric power is generated far away from the places it is consumed. At the generating station, the electric power is generated at 11,000 volts with an alternating voltage frequency of 50 Hz. The power is transmitted to the places of consumption at high voltage to reduce the loss of energy during transmission. The electric power line enters our house through 3 wires, namely the live wire, red wire, the neutral wire, black wire, and the earth wire, green plastic insulation. The live wire has a high potential of 220 volts and the neutral wire has 0 potential. Thus, the potential difference between the live wire and the neutral wire is 220 minus 0, which equals 220 volts. There are different circuits used for different appliances being used in the house. The earth wire is connected to a metal plate deep into the earth to avoid receiving any severe shock in case of any leakage of current while using the appliances. A fuse is an important of all circuits. It ensures that there is no damage that occurs to any appliances in case of current overloading. Overloading occurs when the live wire and the neutral wire come in contact with each other or there is a rise in the supply voltage. In this case, the fuse prevents the circuit and the appliance from damage by stopping the flow of electric current. Did you know? Unlike the field of a bar magnet, the Earth's magnetic field changes as time goes by because it is generated by the motion of molten iron alloys in the Earth's outer core. Fleming's left-hand rule is used for electric motors, and Fleming's right-hand rule is used for electric generators. Separate hands need to be used for motors and generators because there is a difference between the cause and effect of both the motors and generators. Summary. Let us summarize what we have learned. How magnetic field and field lines are generated. The force on a current-carrying conductor in a magnetic field. What is an electric motor and how it works? What is electromagnetic induction and what are its uses? What is an electromagnetic generator and how it works? The use of wires and fuse in domestic electric circuits.